Ladies and gentlemen, welcome to the Boulder Theater and Climate Change on Earth and Other Planets. We want to thank NASA for making this event possible. It is sponsored by the Planetary Society, the world's longest-lived and largest space interest group. We also want to thank the Southwest Research Institute for making this event possible, and also the Comparative Climatology Conference, which is currently underway at the Boulderado Hotel. We do ask that you not use any flash photography. Please avoid that to help out the folks on stage. It is now our great pleasure to introduce the Chief Executive Officer of the Planetary Society. He has just been awarded the Roy Coates Rowe Medal of the American Society of Mechanical Engineering. Please welcome Bill Nye, the Science Guy.
This is so nice. I'm so happy to see you all. I very much appreciate being here. We have four fabulous scientists who are going to talk to you about climate change here on Earth and other planets. I just want to say, everybody's really excited to be here, but you didn't, you didn't need to set the woods on fire. The smoke in the room, to me, just adds another level, another dimension to this thing. This is a picture I took from the hotel across the street earlier today, and if those of you unfamiliar with it, the brown is not normally there. And so I imagine most of you here are concerned about climate change, and I presume there are a few of you who don't believe it's happening here on Earth. And that's good, in a way, because we're going to have questions and answers. We're going to take some time to get everybody's opinions and to, we hope, enlighten you ever so slightly. Let's see if this works. I was traveling the country earlier this year. This is earlier today. And wait, let me just turn it on. Sorry. There we go. Oh, yeah. And earlier this year, we had tornadoes in Dallas-Fort Worth, tornadoes in Ohio. We had tornadoes in Michigan. And then we also, for the first time in my recollection, we got footage of the flying trucks. And this is astonishing to me that no one was hurt in that thing. But this stuff didn't used to happen. I am, if you will, of a certain age, but these things didn't used to happen, especially this early in the year. And so this kind of thing is almost certainly a result of climate change, and I want you all to, dare I say it, change the world. So let's say that this picture of the sun represents the sun. If I'm going too fast, so then this is the Earth. Well, actually, it's a picture of the Earth. If we had the Earth, yeah, I don't think it would even fit in this room, to tell you the truth. So the Earth is, in astronomy, we say the Earth is 1 astronomical unit from the sun. It's astronomical units, the average distance from the Earth to sun, 150 million kilometers, some 93 million miles back in the ancient units. And it's easy to remember. You go up to an astronomer and you say, "Hey, you, how far is it from the Earth to the sun?" And it's just so funny, see, at that point. So then we compare that to Mars. This is a picture of Mars. And Mars is 1.5, on average, 1.5 times as far away. And so, as you might expect, Mars is colder. Thank you, Bill. Yes, Mars is colder. And Mars is so cold. Yes! Not only do they, if there are any of them, Martians, have water ice, they have dry ice, frozen carbon dioxide, like you have at your birthday party in the punch bowl. Maybe not your birth, but mine, yeah. And then this is an interesting effect that we did not explore earlier in the day. Since we changed the aspect ratio of the projector, there's going to be some funny arrows. Funny to me. Mercury is 40%, 0.4 AU. And so, as you might expect, Mercury is fantastically much hotter than the Earth. It's 350 Celsius, something like that. But wait, there's more. Because Mercury has no atmosphere, there is ice in a crater, albeit a big crater, at Mercury's North Pole, if I may. Yeah, surprising result. Venus, 70%. So you'd expect Venus to be a little bit warmer. Quite reasonable, but it turns out Venus is crazy much warmer. And we will discuss that in the coming minutes. So as the traditional sayings go, Mars is too cold, Mercury's too hot, Venus is way too hot, and the Earth, is just right. And this is the fundamental idea in all of comparative climatology. This is the fundamental idea that discoveries made by scientists here on Earth about these other worlds has led us to tremendous insights about our future and what I like to call our place in space. And so it is through this understanding, which I hope will be enhanced tonight, that you can go out and, dare I say it, change the world. So next time you go to Mars, I hope you'll appreciate, if I may, just the beauty of the landscape. I mean, when I see these pictures, this picture's from Mars back in the disco era, back in 1976. You could be working at the car wash. You could be kung fu fighting. Or you could ring my bell, maybe. These would be all things that would be going on. These are songs, ladies. These are songs. There were, it may surprise you, but there were people alive in the 1970s. But Mars is a place. I mean, if you were dressed properly, you could just like walk around. Now, when you go there, let me warn you. So a camping trip, you take food and water. If you go to Mars, what would you, I guess food would be Tang, right? You take Tang. But you also need to take something to breathe because they don't have anything for us to breathe. So caution. Martian atmosphere is less than 1% of the Earth's atmosphere, 0.007. 007? Yes. Atmospheres. And this used to be called millibars, 7 millibars. But millibars have 100,000 in them. They have, if I may, a 10 to the 5th, which is in your future. It's going to be good. The exponents, very cool. I see the pics. Yes, thank you. I got it. Very cool. But the modern unit is hectopascals. So my proposal is we call them HEPs, 7 HEPs. So the Earth is about 1,000 HEPs, 10, 13 HEPs. Mars is 7. So these data are from, God, the arrows don't line up. How charming. These data are from the Sojourner rover in 1997. And everybody in this room was alive, except for a couple, when this number, this is the carbon dioxide in the atmospheres. On Mars, it's almost all carbon dioxide, which is why it's even warm at all. On Earth, it's 0.03% carbon dioxide. 0.03%, if you're scoring along with us, is the same as 300 parts per million. Rounded to 1 digit, rounding to 1 digit, everybody here was alive when that number changed from 0.03 to 0.04. And it is through that, my friends, that we are accidentally changing the world. So when you go to Venus, that's going to be even more challenging Venus is 90,000 atmospheres. 90,000 HEPs, 90 atmospheres. It would crush you like the bottom of the ocean. But wait, there's more. The Venusian atmosphere holds in, so it's Venusian, by the way. In the 19th century, having the characteristics of or pertaining to Venus, an adjective, was venereal. But they had to change that. They had to change it to Venusian. Yeah, I know. It's just one of those things. If you go there, I remind you, it is hot. It's so hot, lead would melt. So if you go there with your fishing weights, you're going to do, fly fishing is quite challenging at that pressure, but the weights would just melt. Your toy army men from the old days would just melt. And by the way, the clouds of Venus are sulfuric acid. You're joking. No, they're sulfuric acid, so it rains sulfuric acid. But wait, the ground is so hot, the rain evaporates before it gets to the surface. So if you have not done this in a long time, I hope you will just recall that era when you couldn't walk on the floor. You can't touch the floor because the floor is like lava. And then you can't drink from the kitchen sink because that's like acid. Well, on Venus, it's really like that, okay? Venus really is like hell by Western standards. And the reason that this is largely because the Venusian atmosphere is so thick and so thick with carbon dioxide. If you showed this picture to my grandfather, he would have been skeptical that it was even real, been skeptical that you could get something that big in space. It's the International Space, well, it's a picture of the International Space Station. It's actually not two-dimensional. And he would think perhaps that the picture of the Earth was out of focus because of that thin, blurry blue around the Earth's edge. But that turns out to be the entire Earth's, or pretty much the Earth's atmosphere. So if you had some extraordinary car on some extraordinary road and you drove straight up at freeway speeds, you'd be in outer space in a couple hours. And that thin, thin layer is what we all depend on to live. And changing that layer just a little bit is changing everything. It is extraordinarily thin. As my old professor, as my old professor Carl Sagan would say, it's like a layer of varnish on a classroom globe. So this is what I like to talk about, for you all to consider, is what I call your place in space. In 1965, I went with my family to the World's Fair in New York City. And they had a couple displays like this. This was of the US population. In 1965, it was 192 million. This number I took off the US Census Bureau website yesterday, and our census now is 313 million. 313 million in the US. Did I say billion a moment ago? I meant million. 313 million in the US. In those days, my father and I were very disappointed because we missed the world tote board, the world display, had just changed from 2,999,999,999 people to 3 billion. Well, as of yesterday afternoon, the world's population was 7 billion. So it has more than doubled in my lifetime. So this change in the world's human population that is so rapid, combined with the extraordinarily thin atmosphere of the Earth, is how we, kookball humans, are changing our climate. Now, you could run in circles screaming. That's one thing that people will try. Generally ineffective. So I want you to consider a few of the following. When you go to Beijing, China, Every apartment building you can see has a solar hot water system on it. Now, why do they put that up there? It takes heat from the sun, evaporates this liquid, which is very much like the coolant in an air conditioning system. Maybe we'll call it a heatant. And then the heatant gives up its energy to hot water, and they get hot water for free. They're not a bunch of hippies trying to live off the grid. Okay, they get it because they do this because the heat is free. I want one of you young people to go into the solar hot water business. Yes, for the betterment of all humankind. That's good. But you would get rich. I don't care about me. It's you. You'd get rich. This is, here I am on the roof of, actually I'm over here. This is a picture of me on the roof of my house, and I have solar panels. I have 4 kilowatts of solar panels. I have a solar hot water system down here, which, by the way, you guys, is a black metal plate with tubes zigzagging through it. It is not, if I may, rocket surgery. It's just plumbing. Who's better at plumbing than the US? Come on. Yeah, I want you, some of you, to get rich on this thing. And then this is the solar tube. It's a brand name that directs light much more efficiently than a traditional skylight because it has these grooves that render it a Fresnel lens, like some of the lenses in these lights. And it directs light down the tube. And I still go in that room and try to turn the light out. It still throws me off. It's in 6 years. Still throws me off. 6 years in a row. But at night, it doesn't. At night, it doesn't do that. Yeah. So anyway, I predict that in the coming years, people are going to come to you with crazy ideas about how to fix, how to change the Earth's climate. And you'll hear the expression geoengineering. And I'm an engineer. I love to make things and fix stuff and tinker. But people are talking about tinkering with the world's climate with these extraordinary ideas. Like we'll get ships to make clouds, and they'll reflect light into space. And these towers then would have to be high enough to reach, you know, thunderstorms, okay? High enough for airplanes to run into them. Oh, I know. We'll fill the ocean with iron and fertilize it, and that'll make algae, and that'll soak up carbon dioxide. So we'll turn the ocean into a giant layer of pond scum. Okay, wait. Okay, no, I got it. We're going to take an airplane and, oh, geez, and fly around. Oh, shoot, this was going to be the big finish. And fly around. Oh, there's what's his name. Sorry. There we go. Okay, wait. I found the button. Yeah, I think. Yeah, see the red light? Now, I know there's some professors here. I just want to tell you that when you do this and then go like that, nobody's getting anything out of it, okay? Just get over it. All right. But the idea is we'll put all this dust in the air that comes out of volcanoes, so then we will have our own sulfuric acid rain. Oh, that's great. No, we'll put giant mirrors in space. That's perfect. What could go wrong? Yeah. Nevertheless, there are people in this room who are going to have to figure this stuff out. You're going to have to decide if any of these things are worth doing. Now, a guy I run across once in a while is quite unusual. But he has one idea that doesn't seem that crazy. If you put bubbles in water, like you see behind these boats, they reflect light, right? But then the bubbles bubblize and they go away. But under certain conditions, like you've ever seen certain spas, certain hot tubs, where the water's almost milky. Well, these bubbles persist if they're small enough, and the water has the right stuff in it, like ocean water. They'll persist for days or weeks. So I imagine, so then they reflect light into space, and that would cool the Earth off ever so slightly. So I'm imagining the World Bubbleator Task Force, controlled by the United Nations bubbleization committee. And then they would regulate the amount of bubbles thrown into space. And I got to say, I've come across a lot of ideas. And this one is so crazy, it just might work. But it might ruin ecosystems, and it might be crazy. But you guys, somebody in here is going to have to be able to vote and evaluate that and vote. Here's what I do want you all to do. We'll have solar panels, we'll have wind turbines, and that's fine as long as the wind's blowing and the sun's out. What we need is a way to store electricity. I drive an electric car, and so people talk about the grid to vehicle, where we would have a grid electrical system so cleverly designed with such good software that it would store energy in people's cars whenever the cars were parked, and we would regulate where the energy is delivered because we know about where everybody's car is parked any time of day. It's like you know how many toilets are going to flush at halftime. People study this. It's their business. So what we would have then are these batteries. This might work. This is a new idea where the batteries are liquid metal. There's a metal right next to tin called antimony, and in Britain they say antimony. And it's like tin, and then you'd have a layer of molten table salt, and then you'd have a layer of molten aluminum. And you just pump electricity into it, and the hotter it gets, the better. And we'd have one of these like in the basement of this building. We'd have it in the basement of every large building. And then we would have this smart grid that would put the energy onto power lines made of nanotubes. These would be the carbon tubes where the electron falls asleep at one end of the tube, has a dream, and wakes up at the other end with hardly any electrical resistance. Now these things don't exist yet, except the cars do, and the wind and solar, that's existing technology. But the solar panels are 15% efficient. Satellites, sometimes they're almost 30% efficient. What if they were 50% efficient, or 60% efficient, or 80% efficient? If you could invent those, you would not only change the world, you would get rich. Ha ha ha! So I am ever so slightly optimistic about the future. Another problem that we at the Planetary Society love to think about is what if the Earth got hit with an asteroid? This would change things. And the scientists who are going to come up here to talk with you in just a few minutes are very, very familiar with this sort of idea. So you'd take a rocket, you'd park it there, and then you'd turn on the rocket motor, and everything would be fine. You see, you don't want to send, Bruce Willis and blow it up, because then you get a shower of rocks. That's bad. And then another idea that the Planetary Society supports research on is we'd have these mirrors that gather sunlight, make electricity to pump or drive very sophisticated, perfectly tuned lasers. And they'd zap the meteorite, asteroid material, and it would volatilize. It would give off some stuff and give it a little momentum and nudge it off course. In November, what did I do? Oh, that's really good, Bill. Wow. Wow. Don't panic. Everything's fine. Okay, cool. In November, I went down to Cape Canaveral for the launch of the Curiosity rover, the Mars Science Laboratory. This is the next rover going to Mars. It'll land Denver time 11:30, I believe it's 11:31, Sunday night, August 5th. Denver, who cares about Denver time? Boulder time, excuse me. It will land Sunday night. We encourage you all. We're going to have Planet Fest at the Planetary Society in several, couple dozen museums around the world, science centers. And this spacecraft is going to go learn about the Martian environment. We're going to learn more about that other world. And the thing that I find so charming about it, it has a laser that will volatilize Martian rocks. So we can determine the isotopes of elements in the rocks. Check it out, people. Humans are sending a ray gun to Mars. Yes. Take that, Mars rock. Yes. But I grew up, my father was quite the amateur astronomer. He spent almost 4 years in prison camp where he had no electricity. And he could name many, many constellations, and he became fascinated with sundials. And so one thing led to another, and there are sundials on Mars. It's right here. And these things, there's 3 of them. There's one on Spirit, on Opportunity, the rovers that are on Mars right now. Spirit is stuck, but Opportunity is still roving. And they carry, for the first time since the 1970s, they carry a message to the future. And this is, to me, inherently optimistic. This is a wonderful thing. Space exploration brings out the best in us. We are trying to know, everyone is trying to know at least 2 things. Where did I come from, and am I alone? And for those of you who have never asked those 2 questions, I encourage you, take the black capsule. Just check out. Just find some rat poison. Just let it go. If you have not asked those 2 questions, I don't know what you're doing here. Where did we come from, and are we alone? And this spacecraft, built by humans, is a tribute to our deep desire to know and understand our place in space. And around the edge of it, in very small letters, it says, we built the spacecraft in our year 2011. It arrived here in 2012. We built these instruments to study the Martian environment, look for signs of water and life, learn about Mars' past, prepare for our future. And then the last thing it says is, to those who visit here, we wish a safe journey and the joy of discovery. And that really is the essence of science, my friends. That is what this thing is all about. And that is why we are all here tonight, to come to know more about our place in space and to share the joy of discovery. Thank you. Thank you. Oh, thanks, you guys. Thank you all very much. Thank you. Wow. Thank you. Our first speaker is another man influenced tremendously by Professor Carl Sagan. And I remember him when these scientists first realized that not only was building nuclear weapons a little bit of a crazy idea to start with, but if anybody actually shot them, you would have a climate change on Earth akin to what killed the ancient dinosaurs. And so to this day, our next speaker is one of the world's foremost authorities on astrobiology. He works right here at the University of Colorado. So ladies and gentlemen, please welcome my colleague, Brian Toon. Dr. Brian Toon.
Well, good evening. We're having a meeting here in Boulder about what we can learn about the Earth from the planets. And let's see here how we get this to actually show anything. There we go. So I'm going to talk to you about one of the more famous problems in planetary science and parallels, which is Goldilocks, the Goldilocks problem, and the habitable zones, and the faint young sun. So these things are all related to each other. So Goldilocks obviously didn't have an interest just in bears, obviously also interested in planets. And she was sampling the planets, and as Bill just mentioned, the Earth is just right. It's in the habitable zone, but Venus is too hot and Mars is too cold. So imagine yourself on a trip to Venus. You're in your spacecraft. It decelerates as you start to enter the atmosphere. Maybe 40 miles above the ground, your parachute pops out, and you find yourself in a smoggy layer, kind of looks like the smoke outside, that kind of smoggy layer of battery acid, so strong it would burn you badly if you got on it, if it got on you. You descend about 10 miles through this smog layer, where you would then encounter clouds of battery acid, which were turbulent. The winds would be jerking you up and down and blowing you back and forth. There would probably be lightning strikes nearby. Then a few miles later, you might break out into the clear and slowly descend to the surface, where the pressures are like being 3,000 feet deep under the ocean. The temperatures are like being in a self-cleaning oven being cleaned. The sky is a rosy, reddish, pinkish glow like the flames of hell. You cannot see the heavens because of the obscuring clouds, so it is a classical vision of hell. On the other hand, if you went to Mars, the sky is pretty clear, maybe a little dusty. Your spacecraft would have trouble even descending. The Mars Science Lab has got an incredibly elaborate means of landing here in August, in which a retro rocket is firing a little crane and then it lowers a lander to the surface with cables. What's the odds of that working, you might ask? But when you got to the surface, if you stepped out, your blood would immediately boil because the pressure is so low. It'd be like being about 40 kilometers above the ground and the earth. The temperatures would be balmy during the day, but at night you'd feel like you were in Antarctica. So obviously, something good happened to the Earth, and something is good happening there now relative to these other planets. What is it? That's the Goldilocks problem. And the habitable zone, of course, is where the Earth is. Is that just because Venus is closer to the sun and the Earth is right there and Mars is over here, or something else? And then we have the faint young sun problem, which is we believe the sun was less luminous early in the history of the solar system. But if we go back to the ancient Earth, it was still just like it is now. And Mars was actually warmer than it is now with lakes and rivers. So why is that? Why were all these planets apparently once habitable and only Earth is left in that habitable zone? Okay, so first of all, why is it that Venus is so hot? So by location, we have Mars out here and the Earth there and Venus over here. Here is the sun. So Venus is getting about twice as much light as the sun. So you think that'd be why it's hot. But Venus doesn't actually use that light. It's covered in this battery acid of clouds. It's a very, very bright object. It wastes most of its energy. And so really, Venus is over here, climatologically. So here we have the sun, Earth, then Venus, and then Mars. So you can see already this messes us up. If Venus is over there, it should be cold. In fact, it's almost in the position of the faint young sun over here. So it should go nice, cold, colder, but it doesn't. It goes nice, self-cleaning oven, then cold. So this is something very confusing to understand. And how we understand this is because of carbon dioxide. Venus has about 100,000 times as much carbon dioxide in its atmosphere as the Earth does, and that's why it's so hot. It's not because it's closer to the sun. Where else do we see a problem here? So if we take the Earth and we keep its atmosphere the same as it is now, and we go back to the origin of life, the time of the origin of life, about 3.8 billion years ago, which is the beginning of the Archean period on the Earth. If we kept our atmosphere the same, the Earth would be a giant snowball. And we know it wasn't a giant snowball. And in fact, some people think the oceans were very warm, 70 degrees centigrade. That's like 160 degrees Fahrenheit. So how is this possible? How could it be that with a faint sun here, maybe 30% as bright as it is now, 70% as bright, it lost 30% of its light, and the obvious solution to that is add carbon dioxide, because we already know that Venus is currently in the place where the faint young sun was, so we can obviously solve this problem by adding carbon dioxide. So this is a somewhat famous story here about how the three planets got to be so different, and it all comes from carbon dioxide and how it moves around on the Earth between different reservoirs. So this is a schematic of the Earth. Here we have the ocean floor and a mantle plume coming up. Maybe this is Iceland or someplace like that. where the mantle is rising up and spreading the ocean. Over here, the ocean is being subducted under this volcano, which is belching gases like carbon dioxide into the atmosphere. The carbon dioxide is then dissolving in the ocean, but it's also dissolving in rainwater. And when it rains, this acidic water, it's slightly acidic, weathers the rocks like the Rocky Mountains or the Himalayas, washes minerals into the sea, which combine with the carbon dioxide and make limestones. So this is a cycle here which is running around, in which we're producing carbon dioxide, then it's going into the oceans, and it's going into the rocks. The rocks are being subducted into the volcano, and the CO2 is coming back out. So what's this got to do with the 3 planets? Well, obviously on the Earth, this cycle has been going like this for 4 billion years, and it has a little thermostat over here which controls it so that the Earth doesn't get too hot and the Earth doesn't get too cold. If it got too cold and the rain came down as snow, you wouldn't weather anything, so you wouldn't lose the CO2 to limestones. It'd still come out of the volcanoes, it'd build back up and warm us up. So there's a thermostat over here. What's this got to do with Venus? On Venus, it's so hot that there isn't any rain falling anymore. The volcanoes have belched out all the limestones as CO2. There's 100,000 times as much carbon dioxide in the atmosphere as on the Earth, but the Earth really has the same amount of carbon dioxide. It's just all in the White Cliffs of Dover, or in your walls of your house, and the gypsum wallboard, and places like that. So Venus is broken over here, not working over there, it's pumping all the CO2 out. What about Mars? Mars is broken over here. It's a small planet. It couldn't keep the heat going to keep the volcanoes going, and so all the carbon dioxide in the atmosphere went down here and turned into rocks or something like that, and it slowly dwindled down to a planet with no atmosphere. So we have a nice explanation of the parallel evolution of these 3 planets. Mars, of course, is a very interesting place. There's lots of tourist spots there. These are giant volcanoes, the Tharsis Ridge volcanoes. These are some of the tallest mountains in the solar system. They dwarf Mount Everest. Here is a Grand Canyon deep gash in the planet that's as wide as the United States. So there's lots of interesting things to visit there, but it's mostly an arid desert. It's a very cold Antarctic, very dry place. Liquid water is not even stable on most of the planet. You can only have vapor or ice. However, it wasn't always like this. We can see signs of climate change on Mars. There are strata of rocks and ice on the planet. You saw some in the movie before Bill gave his talk. They're sort of like the Grand Canyon all stacked up. And those are caused by changes in the orbit of the planet, which is the same thing that have caused our ice ages recently. Well, that's something happening at 100,000-year time scale. But there are also these ancient river valleys on Mars. So you can see this is a big, broad region here with 100-kilometer sort of long river valleys. So it rained here, and the rain came rushing down these little valleys. And here's a long river on the planet. It's about 1,000 kilometers long. So 4 billion years ago, that's what GA means. A lot of Europeans don't know what billion means. So you have to put up a GA so Americans don't know what it means. 4 billion years ago, something was happening here that was very exciting and Earth-like. It was raining. What was it? So lots of people have this image of an ancient Mars with fuming volcanoes and rivers and lakes and oceans. And for those of you with good eyes, there's a little lizard down here. The dream of astrobiologists to have that little lizard there somewhere, if they can only find it, or its skeleton. But there's problems with this. The rivers are really most consistent with an arid environment. Think of Utah. Rather than lots of these lakes and seas. So maybe there are lakes and seas, but maybe not. And there's problems with the carbon dioxide that was supposed to have made this all warm. Where are the limestones? We haven't found those limestones. Maybe the carbon dioxide just escaped to space from Mars. So this is not a problem that's totally solved, but there's a nice consistent story between these 3 planets. And as I mentioned before, the reason it ended is just because Mars isn't very big. It's quite a bit smaller than the Earth, and so it radiated all of its heat away to space and cool off and left this dry remnant for us to explore. So the point I'm trying to make in all this is, yes, Venus is too hot and Mars is too cold and the Earth is just right, but that doesn't mean that these are dissimilar things. The same processes are working in all three planets. We can understand all three planets in the context of one story. There's some details I've overlooked here, but there's one story there that's interesting, and the physics is all the same, and we really understand how carbon dioxide warms things up. Carbon dioxide is a major driver of planetary climates, at least terrestrial planetary climates. There's a bunch of other factors here, like the orbit. Other gases like methane, ice clouds, and water are all major contributors and very confusing, even on the Earth. There are major uncertainties in climate calculations trying to understand these things. Thank you, and I'll turn it back to Bill.
Thank you, Dr. Toon. Thank you. Thank you. Ladies and gentlemen, this is the star-studded comparative climatology cast. If I said to you, October 4th, 1957, Sputnik. If I said to you, June 23rd, 1988. Hang on one moment. Yeah, okay. June 23rd, 1988 is when the next speaker addressed the U.S. Congress about climate change. You mean 2008? No. Do you mean 1990? No, 1988. This guy has been fighting the good fight for all this time. And it really is an honor for me to introduce Dr. Jim Hansen. Is
this it? Thanks very much. Does this work? Maybe it's this one. Yeah. Thank you. About 3 years ago, I wrote a book, Storms of My Grandchildren. And near the end of the book, I had a chapter in which I speculated on what people from another solar system would find if they came to Earth after we had burned all the fossil fuels, if we should be so foolish as to burn all the fossil fuels on the planet. Not thinking that we would ever consider that. And of course, what they found was the Earth was so hot, there was still an ocean on the planet, but the land was so hot that there were no humans left alive. Well, since then, we have begun to develop tar sands and tar shale and hydrofracking to get gas. These are all unconventional fossil fuels which scientists had just assumed, well, we'll never be so foolish as to go after these fossil fuels, because then there's no way that the climate can tolerate those without becoming a different planet. And not only that, a few weeks ago, there was an announcement from Washington that the Energy Department had successfully tested the extraction of methane clathrates, which potentially have more carbon than all of the other fossil fuels put together. So it seems that our governments just don't get it. They don't understand. But what's happening with so far we've burned only a small fraction of these total fossil fuels. But already we can see things happening. Each decade for the last 4 decades, the planet has got warmer. It's now about 1.5 degrees Fahrenheit warmer than it was a century ago, about 2.5 degrees Fahrenheit warmer over land areas. And although that doesn't sound like a lot, and it's smaller than weather fluctuations from day to day, but if you're If you're observant, you can see that the climate dice are now loaded. If we look at the distribution of seasonal temperature anomalies, they form a bell curve. Sometimes you'll have an extremely warm summer, which might be as much as 1 or 2 or maybe even 3 standard deviations warmer than normal. 3 standard deviations is something that happens only a few tenths of 1% of the time. At least that was the case last century. But for the last 3 decades, the distribution has been shifting, so that now the 3 standard deviation anomalies occur quite frequently. About 10% of the area of the land on the planet the last several years has had these 3 sigma anomalies. Last summer it was in Oklahoma, Texas, and northern Mexico. Summer before around Moscow all the way down to the Middle East. They're big areas. And this distribution is going to continue to shift. We know that it's going to continue to shift because the planet is out of energy balance. Because of the fact that greenhouse gases trap heat like a blanket, it warms your body, and that we can now measure that because that energy is going into the ocean, and we're measuring the internal ocean temperature very accurately. So we know the planet's out of balance. It's going to be still warmer next decade. And that's one of the effects of that is to cause a shifting of the climate zones. The subtropics is expanding northward, and that's one of the reasons that Lake Powell and Lake Mead are only half full. And it's the main reason that fires are more frequent, and they're burning hotter, and they're more destructive. It's harder for the forest to recover. Glaciers are melting all over the planet. The Arctic sea ice has decreased about 30% in the summer, at the end of the summer. And those are things which you can see changing at a given rate, but what we should be particularly concerned about, I think, are things that can really go nonlinear and be catastrophic. And we began to measure the mass of the Greenland ice sheet and the Antarctic ice sheet very precisely in 2003 with a gravity satellite. And it measures the gravitational field of the Earth so precisely that you can see changes in the mass of these ice sheets. And they are now shedding ice at a rate of a few hundred cubic kilometers per year. That's still not a lot of sea level. It's about 3 millimeters of sea level per year. But the rate at which they're losing mass is accelerating. And we know that in the last interglacial period that was warmer than the present one, the Eemian about 120,000 years ago, it was only about 1 degree Celsius warmer. We're now within less than 1 degree of that temperature. But sea level then averaged about 4 meters higher, and it was changed by about 1.6 meters per 100 years, going both up and down. Well, that I have made climate simulations in which we put in melting from the Greenland ice sheet at a rate which reached 1.4 meters. By the time you get that much ice melt from Greenland, it will cool off the North Atlantic Ocean by about 10 degrees Celsius. And because cyclonic storms, frontal storms, the storms we get in the winter, large-scale storms, are driven by the temperature gradient, the horizontal temperature gradient. You would get much stronger storms if you had the low latitudes getting warmer because of greenhouse gases, and then these middle to high latitudes getting colder. And in fact, there is evidence that at the end of the last interglacial, sea level went up rapidly by a couple of meters near the end of the interglacial. And there were evidence of very strong storms, including storms that were so strong they threw boulders. This boulder is 400,000-year-old material from the the floor of the Atlantic Ocean, which was thrown up on Eleuthera in the Bahamas by very strong storms that presumably were driven by just such strong temperature gradients. But unfortunately, our governments are really ignoring the science, and they're going right ahead developing all the fossil fuels they can find. And they say the right words. The president says we have a planet in peril, and yet they go right ahead and develop all these fossil fuels. And the tragedy of this situation is that the problem is that fossil fuels are the cheapest energy, and that's why we keep burning them more and more. But they're only cheapest partly because they're subsidized, but partly because they don't have to pay their costs to society. The human health effects of burning fossil fuels, asthma and lung cancer, the many things that are affected by the air pollution and the water pollution from fossil fuels, those costs are borne by the public. And the costs of climate change, which will be borne mainly by our children and grandchildren, or young people here, are also not part of the fossil fuel cost. So what we would need to do to move off of fossil fuels to clean energy is to make the fossil fuels pay their cost to society by putting a gradually rising fee which you collect from fossil fuel companies at the source, at the domestic mine or the port of entry, and you distribute the money 100% to the public, an equal amount on a per capita basis. And that would allow the public to have the means to make the changes that they need to in order to minimize their carbon footprint. 60% of the people would get more money in this dividend than they would pay in increased energy prices. The people who use a lot of energy and fly around the world a lot would pay more than they get in the dividend. But that would stimulate the economy, it would solve our fossil fuel addiction, and it would eventually solve our climate problem. So there's really not much of a downside to it. Even the head of the Republicans for Environmental Protection says this would be a transparent, market-based approach that does not enlarge the government. It leaves energy decisions to individual choices. It's a conservative climate plan. But it's not going to happen unless governments begin to respond to the public's need rather than to the fossil fuel lobbyists who presently, I've gone to 12 different countries, and I find it's not much different in the other countries. Money talks in Washington and the other capitals, and the fossil fuel industry has the most money. We've got to put the pressure on the governments to do what is needed. And it's not a gloom and doom story. It would actually be, if we could do the right things, it would improve the environment and the economy. But we just have to get lawmakers to understand they should be serving us rather than the fossil fuel industry. Thanks.
Thank you, Dr. Hansen. Tell the truth. Fantastic. We can see you. We're right here. Yes, pay no attention to that man there behind the black lectern. So, how many people, what's your favorite thing to drink? Water, exactly. That's right. I know you might rush, but you mix it. Okay. Water is your favorite thing to drink. You and I are made mostly of water. Water is not so much what makes the world go round. it makes the world so that we can live on it while it goes around. Water is the key to life, as far as we know. Water is what makes everything go. So we have now someone we call in science a hydrologist, an ologist of water, somebody who understands and studies waters. Ladies and gentlemen, Dr. Karen Rice.
I'm very pleased to be here tonight. Last October, the media announced that world population reached 7 billion. A few minutes ago, Bill Nye told us that we are now well over 7 billion. This image illustrates the mainstream acceptance of a new geologic epoch known as the Anthropocene. This epoch reflects the enduring effect of human activity on the planet. Almost everything we as human consumers do, from mining and smelting metal ores, to mining and burning coal, to burning petroleum, to growing food, results in acidification. I'd like to acknowledge my co-author, Janet Herman. Our goal was to examine the nature and magnitude of acidification, of these human activities on acidification. To cut to the chase, we think that the planet needs a Rolade. Allow me to explain. It turns out that most of those acid-generating processes from human activities are oxidation reactions, and they involve only 4 elements: carbon, sulfur, nitrogen, and iron. There are 2 types of acidifying reactions, those that generate strong acids and those that generate weak acids. We'll begin with oxidation reactions that generate weak acid. Our largest producer of weak acid is energy production. In this coal-fired power plant, we start with solid carbon, we oxidize it by burning it, and we produce carbon dioxide, which is released to the atmosphere. This is a global map of coal consumption by country in 2009. The color codes are simply categories of convenience where red, oops, sorry, don't have the hang of this yet. Where red indicates the top 3 countries, orange is the next 15, yellow is the next 30, light green is the next 50, and finally darker green is the rest. So what this map is really showing is the top 3 countries are China, the US, and India in that order. And India is about an order of magnitude lower than the other 2. Now, all of this coal consumption results in ocean acidification. This has been called the other CO2 problem. Here's how it works. The carbon dioxide in the atmosphere combines with ocean water to produce this weak acid, carbonic acid, which then dissociates to free protons and bicarbonate. It's these free protons that cause the pH to decrease. While fossil fuel combustion is the major process, other processes contribute, including deforestation, biofuel development, and the very energy-intensive process of cement manufacturing. Now, this is a global map of sea surface pH, and the warmer colors show the more change in pH, the more decrease. You can see that those the larger pH change is concentrated in the colder latitudes, and this is because carbon dioxide solubility is greater in cold water. So on a pH scale, where normal seawater would have a pH of 8.2, we're now globally at about a pH of 8.1. And you think, well, 0.1 pH unit is not very much. But remember that the pH scale is logarithmic. Corals are composed of calcite. Calcite dissolves in acid. If these calcifying organisms cannot maintain their skeletal structures because it's too acidic, they will die. This has implications for the stability of the ocean food web. Now, natural processes do work to neutralize the acidity. Calcite dissolution itself provides a neutralization reaction by consuming protons and producing bicarbonate. But this reaction is limited by the availability of the reactant or the rate of the reaction. And simply put, the neutralization capacity of oceans is inadequate. And on top of that, our trends in human carbon use are that global fuel consumption, deforestation, cement production, and biofuel development all are increasing. Now, let's talk about acidifying reactions that result in strong acid. We're going to switch now to sulfuric and nitric acids. We'll start with acid rain. This was a hot topic in the 80s and the early 90s, but the media has sort of withdrawn attention from it, but that doesn't mean that the effects still aren't measurable. In this schematic diagram of how acid rain is produced, again, we go to the combustion of fossil fuels, coal-fired power plant, as well as the transportation sector. Burning fossil fuels releases sulfur and nitrogen oxides into the atmosphere, which they are then oxidized and hydrolyzed to produce sulfuric and nitric acid. These acids then come out of the atmosphere in the form of acid rain, acid snow, acid fog, as well as by dry deposition. So the acidic return to Earth is more or less continuous. Now on this pH scale down here, carbon dioxide in equilibrium with an unpolluted atmosphere has a pH of 5.6. So it's already slightly acidic. Anything less than 5.6 is considered acid rain. pH as low as 2 has been measured in fog in California. Now this is the pH of lemon juice. Acid rain affects the atmosphere by producing particulates and smog. Acid rain damages the biosphere through direct foliar contact, as well as soil acidification. Acid rain affects the hydrosphere by decreasing the pH in the acid neutralizing capacity of water and causing the sulfate and nitrate concentrations to increase. Now on this little pH scale over here, stream water is widely variable. I'm just using 7 as it's neutral. pHs as low as 3.5 have been measured in streams during storm events, and this has implications for the aquatic organisms trying to survive in those streams. Now there is some good news in terms of sulfur dioxide emissions. If we look at US and Canada and Western Europe, you see that after World War II, the emissions really took off. And in 1970, they peaked. And that was when finally the Western Hemisphere woke up and passed legislation to reduce emissions. In the US, that was called the Clean Air Act. And then emissions immediately started to decline, and then in 1990, additional legislation was passed in the US in the form of Clean Air Act amendments. China, on the other hand, since 1950, has just taken off like a rocket, And I think it's very fair to say that currently they have surpassed the highest peak in the Western Hemisphere. And unfortunately, there's no pending legislation and no curbing action in sight. Now, let's talk about acid mine drainage. This is a coal mine. Coal is almost always associated with pyrite. You dig that coal up and bring it to Earth's surface, that pyrite is going to oxidize and hydrolyze, and you're going to end up with free iron, sulfate, and 2 protons. Likewise, in a copper mine, the ore is chalcopyrite. It reacts with oxygen and water. We end up with free copper, iron, sulfate, and 2 more hydrogen ions. Finally, all of that free iron then reacts with water to form goethite and 3 hydrogen ions. Now this goethite, this mineral, is what this yellow precipitate is in the stream water. And I know if you're from this area, I know you've seen streams that look like this. And so on our pH scale, again, where stream water with a pH of 7 is considered neutral, pH is as low as 2, and stream water from acid mine drainage have been measured. Now here's a global map of copper production by country, and we don't have data for a lot of countries, but that doesn't mean that they don't have copper reserves. They're just not producing yet. Our top 3 countries are Chile, Peru, and the United States, and a very close 4th is China. For both acid rain and acid mine drainage, neutralization by mineral weathering can occur in the form of calcite, consuming protons, that's a buffering reaction, or feldspar, which is the most abundant mineral in Earth's crust. Weathering of feldspar to produce clay or soil consumes hydrogen ion. The problem with these reactions is that the neutralization capacity is limited by the availability of the reactant. There's only so much feldspar and calcite out there, or the reaction rate. It's simply too slow. And our trends in the use of sulfur and nitrogen, in the Western Hemisphere, emission controls were implemented for sulfur dioxide and emissions were reduced, but global fuel consumption is increasing. And for nitrogen, global fuel consumption and the transportation sector are increasing. And our trends in the human use of metals are that global materials and energy consumption both are increasing. Now let's talk about acidification of soils. We grow food crops by applying ammonium fertilizer to soils. This ammonium is oxidized to produce nitric acid. These free protons then percolate through the soil. This is the ion exchange reaction. If we look at this as a soil particle, and this is a interlayer in the clay where the hydrogen ion can absorb to, this hydrogen comes here and gets involved in the mineral structure. In the process, it bumps off a base cation. And so it's the incorporation of the hydrogen ion into the mineral structure that causes acidification of soils. There is a recent study in China that they actually, in 1980, measured a whole lot of soil pHs in croplands, cereal crops, fruit, vegetables, the whole gamut. They went back 20 years later and measured those same pHs, and the pH had dropped from 6 all the way down to 5.2 in a mere 20 years, almost a 10-fold increase in acidity from growing food crops. Now, this is a global map of nitrogen fertilizer application by country. Again, the top 3 countries are shown in red, the next 15 in orange, etc. You get the picture by now. The top 3 countries are China, India, and the US, in that order. These numbers are in the tens of millions of metric tons per year. Next in line, number 4, is Pakistan, and that's about an order of magnitude lower. That ion exchange process that I showed you provides a neutralization reaction. It takes up hydrogen ion, but the result is an acidified soil. And that capacity is limited by the availability of base cations in the soil. And our trend in human use of ammonium is that global food production and consumption are increasing. Our goal was to examine the nature and magnitude of acidification from these human activities. But in order to be able to project trends, we'd like to be able to identify the fundamental driving force. This is one way to look at that. This is the IPAT model that was suggested about 20 years ago, and it indicates that human impact is a product of population measured in number of people times affluence measured by gross domestic product times technology, which can be measured by number of patent applications. Now, if we visualize this as a 3-dimensional box where we have 3 axes, one of them is population, one of them is affluence, and one of them is technology. If we go back all the way to 1900, the box was tiny. It's way down here. And then 50 years later, that box had grown to be this big. And now, 60 years later, the box has grown exponentially. Inside this box are airplanes and cruise ships and toilets and bicycles and sailboats and skateboards and on and on and on, the very stuff of humanity, and that which will help mark the Anthropocene. So if we look at the change in the number of people projected over the next 40 years, we can see that some areas that are not as technologically developed as the US are projected to increase in population. And with that increased population will come demand for fuel, metals, and food. So one way to summarize the effect that humans are having on the planet are that through fossil fuel combustion, we're generating weak acids, which result in ocean acidification, and we're generating strong acids that cause acid rain, which causes soil and freshwater acidification. Through coal and metal ore mining, we're generating strong acids, which cause acid mine drainage, and that causes freshwater acidification. And by application of ammonium fertilizer, we're causing soil acidification. And one way to look at that is through the IPAT model, where human influence is the product of population times affluence times technology. Thank you.
Thank you, Dr. Rice. Thank you. Thank you. You see, a lot of this is science. And this is another case for the magicians out there. It's all done with molecules. And so that is a really compelling thing. I got to say, I'm a little shaken. I need a Rolade. But with that said, our next speaker before we take questions from you guys is a remarkable man. He is. You still work at the Denver Museum of Nature and Science, not too far from here, University of Colorado, and he is the man behind the lectern. Ladies and gentlemen, Dr. David Grinspoon.
Thanks, Bill. Thank you so much. He's not only an astrobiologist, he's the AV guy. Astrobiology is the multidisciplinary study of life in the universe. We study the Earth very carefully because it's the only inhabited planet we know yet. And we study the other planets and all these new planets we're discovering around other stars, very new and exciting development, the exoplanets, and try to understand their environments and where in the universe life might be able to take hold. And so we're interested in the past, the present, and the future of life. I want to zoom us back out for a second to the planetary perspective to sort of wrap up here. Before I do that, let me just mention, speaking of interdisciplinary science, that I am here as part of a conference that's going on this week on comparative climatology of the planets. It's a really interesting and unusual conference in many ways. And one way is that in science we tend to specialize. We carve up into different disciplines. And there's some reason for that. You need to specialize to sort of see farther, to get into the details and learn something. But it's important that we come back together and talk to each other and be interdisciplinary. Sometimes that's where the important questions reside, and the cracks between the disciplines. And NASA is traditionally split up. The science efforts of NASA are traditionally split into 4 divisions. There's Earth science, there's the solar system, there's the sun, which isn't part of the solar system. No, I mean, there's Earth, there's the planets, there's the sun, and there's astrophysics, everything outside our solar system. And what's cool about this conference, and I think unprecedented, is that all 4 NASA science divisions have come together to support this. And I think NASA headquarters deserves a lot of credit for thinking in that interdisciplinary way. And it's been a fascinating meeting because they're experts, not just American, but a lot from other countries too, that really have all these different perspectives. And we're learning a lot from each other about different ways to think about climate and how thinking about the planets can help us think about Earth and vice versa. So it's been really fun. But we've been talking amongst ourselves, and it's so gratifying to see you all here, to see that this place is packed. We didn't know if anybody would be here, and to see that there are that many people. Thank you. It's really wonderful to have you here and have you show some interest in the kind of stuff that we obsess about. And it's important, of course, that we talk to you about what we're doing. And we're looking forward in a little while after I do my spiel to having some discussion and hearing what you have to say. Okay, so the planetary perspective, how can it help us? Now, there's a 50-50 chance that I have the right clicker. Okay, I don't. I told you it was 50-50 chance. But if this one isn't the right one, then I'm really screwed. Yes. Okay. So here's an interesting quote from Fred Hoyle, who was a cosmologist. And before the space age, he speculated that once a photograph of Earth taken from outside is available, that a new idea as powerful as any in history will take hold. And he was right. These photographs of the Earth from space changed us, led to a cultural change. A lot of people say that these views were instrumental in the birth of the environmental movement. I think that was true. Being able to see the Earth from outside and see its smallness and its rarity, its fragility, really moves something in us. We see ourselves in a new way by being able to get outside and look back. Now, in the last 50 years, we've also been exploring the planets, and we now have the ability to look at a family portrait of our solar system. This is something that we've done in our time that people in past generations weren't able to do. Oh, Pluto. Get out of there. There, it's gone. No, it's not. You guys know that Pluto doesn't exist anymore, right? Neil Tyson blew it up. Okay, but we're not going to dwell on that because this isn't all about doom and gloom. We have this beautiful family portrait of our solar system, and it's very useful to us in terms of the knowledge, the perspective on seeing our Earth as one of a family and learning how planets work. We need to learn how our planet works and to understand our role in it. And the only way we can do that is by getting this perspective of seeing Earth as one of an example of planets that have evolved in many different directions, but as we've been hearing, have a lot of commonality in terms of the same physics playing out in different ways. Now, we're lucky to live on Earth because this is a pretty remarkable planet that is unique in some ways, even while playing out the same roles of the same laws of physics. What we have on Earth is these two great heat engines. We heard a wonderful talk today about the Earth's atmosphere as a heat engine. Driven by the sun, the atmosphere moves around. That's the weather. That's one of these two heat engines. But there's also a heat engine inside the Earth. Convection driven by heat, radioactive heat, and heat left over from formation. And you've heard about plate tectonics, where the surface of the Earth moves around and is constantly remaking itself. And we live on the interface between these two great heat engines. And it's really a wonderful thing because the internal heat engine, as Brian Toon was telling us, helps to regulate the climate over the long term by both emitting and sucking up CO2, and it also keeps the surface fresh with nutrients. And the external heat engine supplies us, of course, with energy from the sun directly, but also the weather. Again, we have the hydrological cycle that we've been hearing so much about, the water cycle. And so we really thrive on living at the interface between these two great cycles. And the way we know so much about both of these is really by exploring the planets. By looking at Venus, a similar-sized planet, remarkably similar. Venus and Earth are almost identical twins in many ways. We have a very similar heat engine in the interior, and a lot of the same processes remaking the surface and going on in the interior, and yet they're different in somewhat mysterious ways, and understanding that difference is really giving us a whole new perspective on the Earth. Similarly, we've learned so much about the atmospheres of the planets and the way they move around, the dynamics, the way the weather works, the way radiation travels through the atmosphere and affects the surface, again, by studying the other planets. In planetary science, astrobiology, we also have the perspective of deep time and seeing the present moment in the whole long sweep of the Earth. Of course, geologists have been thinking about deep time for a long time, but through the space program, of course, we've been able to go to the moon and learn things about the early chapters and the other planets, and look at meteorites and asteroids and learn about the early chapters of our own history that have been destroyed by the very vigorous activity of those heat engines on the Earth. An active planet like the Earth destroys its early history because there's so much going on at present. And so sometimes by going to the moon and going to the other planets, we learn about those early chapters of Earth that the pages of the book that have long disappeared from Earth. So a perspective on deep time. Don't worry, I'm not going to describe all this in detail, but this is just, these are some of the sort of the Earth's greatest hits, the big, some of the major events of Earth history, and I won't go through them all. They're things that some of you have heard about, but what I do want to point out is that in a way we can look at this, along the bottom here, we can look at this in very broad strokes. We can understand this sequence of transitions where very early on the geosphere gave rise to what people often call the biosphere. The origin of life happened early on Earth, sometime around 4 billion years. As soon as things settled down enough so we had a reasonably stable surface, that early on we have evidence of life. So life happened very early on Earth, which seems to be a clue that life perhaps happens easily on a planet with the right conditions, and maybe a clue that our search for life elsewhere will be fruitful. And then a lot of things happened that I won't go into detail about, but very recently something new has happened on the Earth. And some people describe that as the biosphere giving rise to the noosphere. That is, and this phrase originally comes from Teilhard de Chardin, and I think also Vladimir Vernadsky sort of co-invented it. But this phrase sort of means the sphere of influence of mind. There's something happening on Earth now that's new and unprecedented. And the previous speaker, Dr. Rice, referred to it as the Anthropocene era, that we've almost entered, that we, in a sense, we've entered into a new geological era where humans are rapidly remaking the Earth, and human activity has taken over as at least one of the dominant drivers of change on the Earth. If you were a patient extraterrestrial who had been watching the Earth for all these billions of years, and let's say you were watching the night side of Earth, you would have, for a long, long time, seen mostly just darkness on the night side of Earth. There would have been the occasional lightning flash, sometimes some aurorae. More recently, forest fires. But remember, trees have only been around for a few 100 million years, so most of that time you wouldn't even have had that. But you would, in more recent times, since the continents got forested, you'd see some flashes of light, but it would be mostly dark. And then very recently, and very suddenly, this happened. You would have seen the coastal areas springing to light, and these strange networks of crisscrossing lines covering the continents. Something very new and unprecedented is happening to the Earth. Now, astrobiology is the study of the relation, in a sense, is the study of the relationship between life and planets. And in a certain sense, with the Anthropocene, with the noosphere, these rapid changes, we've entered a new chapter in that relationship, in that long relationship of life and the planet co-evolving together. I think if we look at that relationship and we look at the long history of global changes on the Earth, we can classify all the changes, the major changes that have happened in Earth history, into 4 kinds of global changes, each distinguished by a different role that life is playing in that change. So the first one I'm calling natural disasters. That is, as the bumper sticker says, stuff happens. Sometimes a planet can be in the wrong place at the wrong time, and an asteroid will hit it. And a big one will do very nasty things, like the asteroid or maybe comet that hit the Earth 65 million years ago and wiped out the dinosaurs along with 90% of the other species on Earth. So life had nothing to do with this. Life just had a bad day that day. This is, in the true sense, a natural disaster. And there are other examples as well. The second class of global change I'll call biologically induced. And that, a great example of this is the rise of oxygen, when all those irresponsible cyanobacteria and green plants came along and changed the Earth in this dramatic way with oxygen rising up. It was a disaster of unprecedented proportions. We love oxygen because we've learned how to use it. That is, we've evolved to use it. But oxygen is a poison to organic life, and when oxygen rose in the atmosphere, it was disastrous for many kinds of life, and there was a lot of extinction. And so this was a major global change that was biologically induced. And there are other examples as well. I'm not going to go into a long list because I want to move along. The third type of global change is the kind that we see happening now, and it's what I'll call inadvertent change. And represented here by traffic, we now have a species that's very clever at inventing new technology and clever at solving scientific problems and doing other things, but perhaps not very wise and thoughtful, and doesn't have a lot of control over its global actions. So we're doing these things, and this is somewhat different than biologically than this kind of biologically induced change, which is done by microbes and plants, because these are so-called intelligent species, obviously doing very clever things, and yet inadvertently, without any planning or forethought, changing the planet in a dramatic way. Now, I think there's a fourth kind of change, and that's intentional change. And that's the kind that we have to move towards. And I think it's as an astrobiologist, I think about global changes not just on Earth, but on other potential planets with life out there in the universe. And I think that this transition between inadvertent and intentional change is a really important branching point, perhaps, in planetary evolution, other places as well. And an example of intentional change, and it has happened already, at least to some degree, a great example is the ozone hole, which you've heard about, which has been getting worse and worse and worse, and was recognized in the 1970s, largely as a result of planetary exploration, by the way. People studying the atmospheric chemistry in the upper atmosphere of Venus said, hey, this chlorine is reacting with oxygen in weird ways. Oh, could that be happening on Earth? Oh, and led to the discovery of ozone destruction. But the good news is that through international treaties and various agreements and various changes in behavior, that we are fixing the ozone hole. It's going to take a lot longer, but things have been moving in the right direction. It's an example of intentional global change to fix a problem. Now, there's other examples of this fourth type of global change, where truly intelligent life acting with forethought and aware of its global role and responsibilities, and acts with an awareness of global consequences of its actions. Ozone replenishment is one example. Another example would be the intentional halting or reversal of industrial global warming, which, unlike the ozone replenishment, is not happening yet, but it's currently under discussion, and the discussion is at least a step. There are other examples. The terraforming of Mars may seem like science fiction, and fortunately it is science fiction. That is changing Mars so that it can support life if it turns out to be lifeless. And I don't think it's a good idea to go up and try to terraform Mars now, but I'm glad people have been studying the problem, which some people have been for a while, because it's a way to think about intentional global change. How would we go about intentionally altering the climate of a planet, rather than inadvertently, accidentally altering the climate of a planet? In the long run, we're going to need to learn to do this, because the Earth's climate is capricious. You've seen those squiggles that the climate deniers say, oh, it was hot, it was cold. It was. It's just on a much longer time scale. The problem now is that we're forcing it on a very short time scale that we're not prepared to deal with. But in the long run, the Earth's climate does change by itself, and if we want to have a truly sustainable civilization for a long time, we will have to learn to prevent ice ages. And eventually, in the very long run, our sun is going to make the Earth uninhabitable in about 1 billion years. Now, that's a long time. We've got more immediate problems. But again, thinking as an astrobiologist and the problems that life will ultimately encounter as it evolves on planets, we think about such things. And the mitigation of the eventual, inevitable runaway greenhouse due to the warming sun, which won't be necessary for a long time, but it will be absolutely necessary in the long run for life to survive. So these are all examples of what I would call intentional change. Now, I'm going to wrap up, but at the very beginning, Bill Nye mentioned these great questions. Where do we come from, and are we alone? Now, when we ask, are we alone, we sometimes think about finding microbes on Mars, but a lot of us think the most exciting application of that question is the question, is there other intelligent life? Or when I say other, I'm perhaps self-aggrandizingly calling us intelligent. Is there intelligent life out there? Is there anybody to talk to? I think that ultimately the answer to that question has to do with this transition. The survivors will be the ones that learn how to become intentional about their global actions. And if we want to be survivors and not a statistic, then we need to make this transition. And the question of whether or not this sequence of steps is a common story, to me, is very closely related to this question, are we alone? If you do the math, it turns out that, and you actually try to calculate the number of civilizations in the galaxy, which you can do because we know the number of planets now, we know something about what those planets are like, we can make some calculations of the probability of life and all these things. But it turns out when you do the math, it really hinges on how long civilizations stick around. And that will depend on this. So I believe that out there probably are a lot of civilizations that have made this transition. I don't know if we will. I think we've got a shot at it, and it's our responsibility to try. But I believe that it happens. I believe that there is life out there that has solved this problem. So as this sort of cosmic optimism, if you want to call it that, was summed up perhaps best by Franz Kafka, who said, "Oh yes, there is lots of hope, but not for us." Anyways, A brilliant prophetic Englishman once said, "There is no way back into the past. The choice is the universe or nothing." And I'll leave you with a quote from a wise guy, American, who said, "More than any other time in history, mankind faces a crossroads. One path leads to despair and utter hopelessness, the other to total extinction. Let us pray we have the wisdom to choose correctly." Woody Allen. All right, thank you very much.
Thank you, Dr. Greenspoon. Thank you. Let's have a hand for all of our speakers. Dr. Toon, Dr. Hanson, Dr. Rice, Dr. Greenspoon, me. So, in moments, as if by magic, a table will be brought forth into the light, and we will answer your questions. I see people gathering at microphones even as we speak. Lindsay. It's not Terry. Is it Mitch? What's your name, sir?
Sean.
Sean. And Lindsay. Sean and Lindsay, ladies and gentlemen. Yes. So our distinguished panel is going to come up here and panelize distinguishingly. And we very much look forward to your questions. Let me say, by long experience, these things are much more interesting for everyone if you have a question, rather than something that's not a question. So if you go rambling, especially on the war story, the moderator, shown here, may discourage you. So thank you all very much. Please find the microphones and let's get started. I'm brightly lit, but I believe over here is our first question.
Hi, my question's for Bill or David. And with NASA discontinuing the shuttle program last summer, and with the rising success of commercial space exploration, what role do you think that NASA and other government space agencies are going to play while my generation grows up?
Oh my. So everybody, let's start with this. The space shuttle cost all in about $1.5 billion a flight. So it was not a good value. Retiring it was just something you had to do. Your car gets old, you got to get a different car. Bear in mind that the great success recently of SpaceX is fantastic because these people used technologies developed many years ago and upgraded them, and it's a real factory approach, a real assembly line approach to making rockets to take people to Earth orbit. But keep in mind that if you want to make discoveries on other worlds, there is not a profit to be made. SpaceX is in this business, I don't want to shock you, but there's a lot of satellites put into space by the Air Force and what are called OGAs, other government agencies. These would be spy satellites, and then a tremendous number of communication satellites. So SpaceX sees this as a way to make money. Then the other really well-known space industry entities right now, or organizations, are people that want to take people into space, into where the sky is black and you see stars. And I don't want to forget anybody, but Virgin Galactic, Sierra Nevada Corporation, X-Corp, and Blue Origin. Yes, Blue Origin is quite secretive. Blue Origin is the same organization as Amazon.com. Same company, same management. Anyway, those are different roles than going to Mars. And when it comes to how many people want to be astronauts? How many people don't want to be astronauts? Anyone? Anyway, I applied several times. It's quite difficult now, you know. Have you applied, David? You must have.
Well, I've trained for suborbital.
Oh, you trained for sub, you're ready to go. Suborbital means you don't go into orbit. To go up into space where the sky is black takes about 1/9 as much energy as to go into orbit. But to go to Mars takes another extraordinary step in energy. And it's much more complicated. So in your lifetime, it is not beyond beyonding that we will find not just evidence of water on Mars, but evidence of life on Mars. I'm imagining some ancient stromatolite, some ancient pond scum that's turned to rock, lithified, I believe. And that would change the world. That would completely change the world. It would be like discovering that the Earth is round. It would be like discovering the Earth goes around the sun instead of the other way around. It would change everything. So you are living at a time where access to low Earth orbit is going to become cheaper, but the challenges of getting out to these extraordinary worlds and making extraordinary discoveries are really at risk. Right now, the U.S. government, which is still the biggest still runs the biggest space agency in the world, is cutting the budget for planetary science. So we at the Planetary Society encourage you all to become members and go stop at our table on the way out and pick up a copy of the Planetary Report. Because one of the things we do is advocate for space exploration. You are living at the most exciting time in space exploration. Way to go. Way to be born when you were.
Thanks, Bill Nye.
Yeah, I would just add that, that the role of NASA is to explore and keep going to places where there isn't an immediate profit to be made. Go to Europa, go to Titan, go to Mars. But it's fine with me if companies want to take over the trucking business that basically is what the shuttle was doing. We're all nostalgic about the shuttle, but it was time to retire it. It was getting old. And as long as NASA keeps exploring and keeps helping to monitor global change on the Earth, along with the other agencies that do that, then it's okay with me if NASA gets out of the trucking business.
Should we go over here?
Yeah. This one's probably going to be very short. I just wanted to know when the age of like the Anthropocene began, if it was recent, like 1980, or if it was like hundreds of thousands of years ago. And I just wanted to know whether it's really like a topic for any serious discussion or anything like that.
Great question. Way to go.
So there are there are scientific bodies that decide on geologic eras and geologic names, and there's a debate in those bodies at the moment about whether we have entered this new era, and to have a geologic era, it has to leave a mark in the rocks. And so the question is, when did we first leave a mark on the rocks? Is it when we started to produce large amounts of carbon dioxide in the atmosphere, which have acidified the oceans? Or was it some other time when people first started fires and left layers of charcoal around? Or is it sometime still to come slightly in the future when we do something else which will affect the whole planet and its geology? So the definition of Anthropocene and the use of that name is something that the geological community hasn't really officially designated.
So we should check in 10 million years or so?
Exactly.
It's funny, you should ask that, because just the other night, a couple of us who are here for this meeting were drinking a couple of beers and arguing over this very question: when did the Anthropocene begin? Now, young man, I'm not advocating that you drink beers, but I think that you should have animated discussions. And my thought was that it maybe would be when the first atomic bombs went off, and that the signature that would leave in our soil. But other people were saying, well, really, like you were saying, it's about a layer in the earth, and it's sort of all the junk, all the crap that humans leave that ultimately will be a layer in the soil. And we agreed that really we can't decide when it begins, that 1,000 or 1,000,000 years from now, people will look back and they'll see it. And just like we have imprecise ideas of when other geological ages began, we can't say what day they started. We can say what, except for maybe the Cretaceous Tertiary extinction. That started in an instinct. But the point is, we can see it happening, but we probably don't have the perspective right now to say exactly when it began.
Karen, you going to say something about the Anthropocene?
I can add to that, and probably what will be most evident in the geologic record in the future is that we will see, or future geologists will see, mass extinctions.
Right.
So does that mean me? Yeah, that's where you see that this is evidence in the rocks of mass extinctions. That is a great question. That is deep thinking. Thanks. Very nice. Thank you.
Thanks.
Sir, over here.
So this question is maybe mostly for Dr. Hansen, but I'm happy to hear from anybody on the panel. I'd like to hear what your thoughts are on Bjorn Lomborg's observation regarding the political pressure to cut carbon emissions and change energy production, and the things that everyday citizens do to reduce their carbon footprint as being ultimately something that should be done but is not economically feasible or going to have a significant impact on temperature.
Lomborg, I think, makes a fundamental mistake.
Here, spell it out a little bit. What is his assertion?
Well, his assertion is that it would cost a lot of money to deal with climate change, and there are other problems on the Earth, so let's not waste our money on dealing with climate. But the fact is that moving toward clean energies and energy efficiency by making the fossil fuels pay their honest cost is actually going to be very economically stimulating and produce a lot of good jobs. So it really is not, there's really not a conflict between strong economy and a healthy planet. And there's really a false assertion that he's making. And likewise, he's saying that, well, there are a lot of poor people in the world, and we should rather spend our money there. Well, in fact, the best we can do is improve the economic well-being of the people in the world, and that can best be achieved by moving off of dirty fuels onto clean energy and energy efficiency.
But their level of affluence, though, increases their carbon footprint, though, correct? Isn't that part of the formula?
It doesn't need to. We can move completely off of fossil fuels. In fact, we have to. If for no other reason, eventually you're going to run out of fossil fuels. But if you wait until that happens, well, we're really in trouble. But no, there's no reason that they need to follow the fossil fuel addiction that the United States developed, and which is continued by the people who are profiting from the addiction. There's no reason that other countries should want to go down that path. But in order to make that happen, you're going to have to make fossil fuels pay their true cost.
Yeah, linking this question back to the other one, people don't realize the time scale of carbon dioxide in the atmosphere. So when I drive home today, I'm going to release carbon dioxide from my car, and about half of that's still going to be in the atmosphere for about 50 years. About 20% of that is going to be in the atmosphere for tens of thousands of years. So this is the first time that human beings have changed the planet on a geologic time scale. And so those carbon markers, are going to mark the Anthropocene because it's a geologic time scale that's involved here.
But here's what I always say as an engineer. There's opportunities. Somebody's going to get rich. And as a guy who grew up in the United States, I was born here, I don't know any better, as a patriot, I want the United States to be the world leader in this new technology and export that technology to improve the lives of people everywhere. The longest journey begins with a single step. I think back at the real fear I had as a little kid when people talked about nuclear war. My family went shopping for a fallout shelter. It was like this was going to be fine. You just live in this thing. And I was terrified. And it is that sort of fear that motivates you, though. It's that sort of fear that drives you forward. And it's that sort of thinking that allows you to innovate, stimulates you. We can change the world, everybody. We can do this. So, as we say in comedy writing, if you buy the premise, you'll buy the bit. But if you don't buy the premise, nobody's going to laugh. And so I don't buy this guy's premise.
Bill and the audience, I'm apologize, but I'm going to have to leave. I have a plane to catch.
Oh, you have a plane to catch. Did you bring a big net? Anyway. So, come on. That gets a laugh. See, they bought the premise, and then... Well, Dr. Hansen, thank you very much for coming. Please don't be late for your plane. You are the man. You are the man. This is the guy. So, those of us of my age are of the space generation of some people in the front row here. You are the climate generation. And Dr. Hansen, to me, was the guy who marked, if we're marking things on rocks, marked the beginning of that. He's changed the world. Man in plaid, man in plaid.
I have a question for either Dr. Rice or Dr. Nye. If we were to, say, build a spaceship where human life would be transferred and basically synthesize an environment for living, like basically a man-made planet, what would some key components be to survival and temperature and climate?
Oh, don't worry about it. No, that is a great question, and many, many science fiction stories have been written to address this question. And I will say, just overall, you need food, water, and shelter. You got to keep warm. It's surprising what small temperature changes make humans uncomfortable. But what is also surprising is people choose to live all over the world in ice and deserts. It's extraordinary. So I encourage you to try to write a science fiction story with that as the idea.
All right, thank you.
Wow, cool. Pluto. Back in my day, Pluto was a planet. Your T-shirt. Yeah. I have no problem with Pluto not being a planet. It's fine with me. But if the Astronomical Union insists on using dwarf planet, I'll go. Okay, dwarf planet. I'll go with them. That's a good shirt. Yes.
So my question is primarily for Dr. Grinspoon, but anyone can really tack onto this. So my question was, so when you were telling us about what you were saying, you said that one of the intentional changes we could make was eventually preventing future ice ages. How would we be able to do that?
We're well on our way.
Yeah, well, fortunately, we have a long time to think about that one. We obviously have more immediate problems, but it's good that you ask, and it's good that we think about it. You know, I think there's this whole spectrum of sort of levels of control we could exercise. And the first thing we have to do is gain some control over ourselves and stop inadvertently veneriforming the Earth. That is, making Earth more like Venus. But then beyond that, we do have to think about, okay, now whether we like it or not, we're sort of the ones in charge here. If we want to have a human civilization, we can't go back to the past and say, well, let's all, I mean, we could, but it would be pretty radical. We'd have to get rid of most of the population of Earth if we want to just go live like our ancestors did who didn't have technology. I don't advocate that. And if we don't do that, then like H.G. Wells said, our choice is the universe or nothing. And so we have to accept our role as sort of, in a certain sense, managers of the planet, hopefully wise managers. And then, so we have many thousands of years to work this out. And so, for example, we've been learning a lot about the greenhouse effect. And my favorite way, if I had to, if you asked me today, unfortunately I don't have to decide this today and I'm not the one in charge, but if you asked me, how would I prevent the next ice age, I would say, well, let's increase the greenhouse effect a little bit and warm things up. I would not do that by pumping CO2 into the atmosphere because as Dr. Rice has ably told us, CO2 does other nasty things. It acidifies the oceans. It destroys coral. It's in large quantities. it's bad stuff. But we know how to make other gases that absorb much more efficiently, some artificial gases. And of course, one of the best ones is the chlorofluorocarbons, which are also bad because they destroy the ozone layer. And so we don't want to use those to pump up the greenhouse effect. But I think there are ways that we could modify the atmosphere if we had to prevent an ice age. Do we know enough right now to do this? No, we don't. But that's why we're studying the other planets, and that's why we're studying the way the Earth works. And I think if we're around for that thousands of years that we have to worry about an ice age, that we're either going to gain that wisdom or we're not going to be around.
Thank you.
Very nice, very nice. Man in hat.
Yes. I wanted to thank you all for coming and speaking tonight and your contributions to the sciences and engineering. My question has to do with nuclear fusion. I'm an up-and-coming physics student and trying to help with the climate change and releasing the world from foreign oil addiction. And I was wondering what your thoughts were on the plausibility and the actual feasibility of nuclear fusion being a real source of energy in the future.
Since I was in school taking physics, nuclear fusion is 40 years in the future. At any time, it's 40 years. But I met a guy the other day who said, no, it's 50 now. It's 50 years. But with that said, when I was young, the universe was expanding. Discovered the Big Bang. All the stars are moving apart. They must have started somewhere. That's the Big Bang. So everybody then inferred quite reasonably, figured, well, if they're all expanding, they all got gravity, they should all slow down. Everything should slow down. Well, just 2004, I guess, they finished. These scientists, I interviewed a guy named Saul Perlmutter, just one of the people, won a Nobel Prize. They went out to study how fast the universe was slowing down. This will be fun. Let's take a few minutes. We'll just automate telescopes all over the world to find supernovae, exploding stars, and we'll record them really fast, and it's going to be fabulous. So then they analyzed how fast everything was slowing down. And it wasn't slowing down. And they analyzed it again. The guy told the story. He's very cool on camera. He's very compelling. How they thought there was an error in the software, some minus sign they'd put in someplace. No. The universe is expanding. It's accelerating. And do you know why? Nobody knows why. And so it is quite reasonable that people will discover, if I can use the term, a whole new physics, a whole new aspect of science that might influence the possibility of fusion in a controlled reaction here on the Earth's surface. We have a fusion reactor at a safe distance. We have the sun. And that's hard to put on the Earth. It's very challenging. You probably only do it once. But it is not unreasonable to me that a new physics will be discovered that will make something like that possible. In the meantime, nuclear fission seems like such a great idea. You dig this stuff up and you let it get hot and you boil water and you make electricity. It's going to be great. But it turns out burying it, getting rid of it's really complicated. And the other thing is when stuff goes wrong, it just goes so badly wrong. I mean, we have 432 commercial nuclear power plants now. There's some military ones, but 430 something. But there's 800,000 oil wells. But suppose we had nuclear power plants on the same scale as oil wells or even oil refineries. If you had tens of thousands of nuclear power plants, you're going to have accidents. Oh, man, that is a problem. It's a problem. Maybe you'll figure it out. Anybody else?
Well, just the attraction of fusion, for those of you who have a strong reaction to the word nuclear, and I think we all do to some extent, is that fusion would be much cleaner. The sun burns hydrogen into helium and releases all this great energy. That's nuclear fusion. It's not magic, it's physics. It's just being able to do it in a contained way is difficult. But I think it's possible, and I think that is the kind of breakthrough that would be a game changer in this game that we're in, whether we like it or not. And so I encourage you to to keep at it. And if that's something you're interested in, work on it and find a solution.
So notice this is astrophysics that would make discoveries that affect particles, affect the tiniest. It's amazing. It's quite a cool thing. Man in they have the shirt pockets, snap pockets. Yes.
So we're at about 390 parts per million carbon dioxide right now. Is that right? Somewhere
yeah, some people say slightly higher, but it's about that. Yeah.
Some scientists think that at 550, life as we know it won't be that fun, and that trends right now that even if we put on the brakes as fast as possible, we probably can't prevent ourselves from reaching that in the middle of the century. I wonder if you guys think that's true. And then the other thing is, in the late Cretaceous, like 70 million years ago, weren't there temperate forests on Antarctica? And, and wasn't the CO2 levels like 2,000 parts per million? I wondered, I don't know exactly what, but much higher than it is now. And I wondered, how did the planet recover from that episode?
Well, the word recover, or the whole thing was so much more slow. It's the rate that's so troubling. It's the speed at which things are changing.
Earth has a natural thermostat that Dr. Toon described. It's just that it takes 1 million years for the Earth to suck it up, and we don't have that kind of time.
Is it 1 million or some other?
It's a very long, so the cycle I described is a very long-lasting cycle. But if you look at Earth history, this takes since the last 600 million years when there have been organisms besides just simple creatures. In that 600 million years, 90% of the time there have been no polar caps. And we actually are living in an ice age right this minute. So when there are polar caps, you're in an ice age. Of that 10% of the time when there have been ice ages, 90% of that time the ice has been more advanced than it is now. So we're in a period that's pretty rare in Earth history when the ice has not been too advanced but has been present. So we're in an unusual world. We've lived in this world. We've built all these cities and other things. So the Earth biology is perfectly fine with higher CO2. We just won't have any polar caps. And that's a normal state of the Earth. And if we go to that state of the Earth, the oceans will be 300 feet higher. I don't think Boulder will be waterfront property. But you won't be living in Miami. You won't be living in New York City. You won't be living in New Orleans. Almost all of the cities that are highly popular in coastal areas will all be underwater. And, so that's the real problem with the greenhouse effect. It was to destroy our infrastructure. It'll be a tremendous reordering of life. And lots of life, as has been mentioned here, can't quickly adapt. If you change something over, a short period of time, really geologically, even thousands of years, you see bursts of evolution, things change, plants move, animals go different places. But you do it in 100 years, and you cause massive disruptions to the ecosystem. And of course, it's not just carbon dioxide that we're messing up. We're occupying all the land. We're causing a mass extinction largely because of land use changes. There's, even around here you can see, we got bears in the city and deers in the city and all these other creatures that we're displacing from their environments, and they're trying to come into the ones that we've taken away from them. And the same is true with people. I'm an American Indian myself, and most of you people came in and displaced me. We're going nearly extinct. So those are the kinds of problems we're having. It's a time-scale human infrastructure problem and extinction to everybody else and all the other creatures.
Thank you.
By the way, that last questioner is a famous writer named Peter Heller, and he's got a novel coming out this summer, a post-apocalyptic novel called The Dog Stars, and it's going to be awesome, so watch for it.
Nicely plugged. Nicely plugged. Did I mention the Planetary Society?
He'll give me a check later.
Man in green.
This question is probably for Dr. Rice. In your presentation, you talked a lot about the bad things acidification is doing to the oceans. But frankly, I was quite surprised to see that biofuel development is such a big problem. Now, granted, there are big problems with the biofuels industry today. For example, food is often being sacrificed for fuels, there's massive deforestation, and so on and so forth. But do you believe there's a future for advanced biofuels that are currently only perhaps in research and development areas right now?
The problem that I mentioned with biofuel development is that it's an energy-intensive process. So actually it takes more energy than to produce it than you get out of it. So that was my point.
Sure, but do you believe there's a future in biofuels?
There's bound to be. Once again, you know, echoing what Bill Nye would say is figure it out.
Maybe you'll be the one.
Maybe you'll be the one.
There's an X Prize that they're considering. This would be offering millions of dollars for somebody who can make a toilet that produces fuel. I don't want to shock any Coloradans, but you know, sometimes you can burn certain things you find in the field after they dry out. Cow waste is burnable. It's reasonable that human waste would be burnable. And that would be, if you could do it less inefficiently, it might not be bad. Maybe you will be the one who figures it out. Maybe you will win the prize.
There are other problems with biofuels too. People are planting oil palms, places that are displacing other crops that people need for food and causing other environmental problems. And you know, this unintended consequences. One of the challenges here is that there is no perfect power supply. You know, even things that seem good, they cause some problems. And so this is partly why this problem is really tricky.
Thank you.
Striped man.
What would happen if if all the planets started circling the sun in a square?
In a square?
That's for you.
If all the planets start circling the sun in a square,
then they wouldn't be circling.
Well, that's for one thing. But you are living at an extraordinary time, my young friend. When I was in school, everybody figured quite reasonably that once the planets are put where they are in their different orbits, they would stay there. What's the big deal? Mercury's small, goes around the sun fast. Jupiter's huge, goes around the sun slowly. Pluto, way, way out there, goes very slowly. Many hundreds of Earth years to go around the sun. But it turns out it hasn't probably always been that way. The gravity of these different things causes them to sling each other back and forth like when you grab each other on an ice rink. So that question, squaring a circle, people bought the premise and you got a laugh, very nice. But it's not that crazy. So now as we study these other worlds orbiting other stars, we believe we are making discoveries about the nature of our place in space and how the Earth ended up just in this perfect place to have liquid water for you and me to be made of. That's pretty cool. That's actually a pretty cool question.
And orbits are not circles, so you're on the right track.
Yeah,
they're not circles.
quite.
They're these slightly egg-shaped things called ellipses. You know that, don't you?
And a circle is in the family of ellipses. It's just,
it's a special
perfectly round. Yeah, instead of having the whoa quality. It's actually a pretty cool question. Yes, Blue Man.
All right, so my question's for Dr. Rice. This coming fall, I'm going to CSU to study watershed science, and I was just curious from hearing all of your guys' talk about how there's water on other planets, if there are people now or there will be people studying specifically water on other planets and not on Earth.
I think that's already going on. I do know that there's research at UVA where they're looking at the landforms of Mars and trying to figure out what the water patterns were.
Furthermore, there's glaciers under the sand on Mars. So I'm all kooky for Curiosity, the rover, crazy for it. But I want to get an explorer there, either a robotic explorer or a human in the right suit, to go near the equator to some outcropping where the super salty, slushy Martian water is oozing out of the cliff. And there we might find Martians, little microbes from Mars. Bah, ha, ha, ha. So right now, astrobiologist Dr. G straightened me out, but water is still the best thing for a living thing that we can think of.
Yeah, as far as we know. And that we can think of may be the key. Maybe we're just not that smart. But when we search for life elsewhere, we're very much searching for water because at least as far as we know now, that's what life needs. So we have to keep an open mind because we only know one planet with water. But we're very interested in water for that reason. And yes, people are studying water on Mars. People are studying water in the icy moons of Jupiter and Saturn. And people are even studying flow that is like water flow, but other liquids. There are rivers on Titan, Saturn's moon Titan, of methane, and people are studying that and comparing it to the water cycle of Earth. And on Venus, believe it or not, we see structures that look like rivers, that are rivers, but they're rivers that were carved by some strange kind of lava that flows for thousands of miles across the surface. So study your hydrology, apply it to problems of Earth, but if you're interested, yes, there are applications and there are places you can go and study hydrology on other planets.
All right, thank you very much.
And the big picture is you go studying that stuff on other worlds, you don't know what you're going to find. You don't know what you're going to discover. People ask me that about the space program all the time. Why are you sending a spacecraft there? What are you going to find there? We don't know. That's why we're going. So you don't know what you'll discover. That's actually pretty great. Turquoise woman.
How do wildfires affect our global climate?
Well, there's data that shows that although carbon emissions from industry in the United States, for example, have decreased recently, which is an interesting and important thing because carbon is it's not a greenhouse gas, but it's warming the Earth because it absorbs light because it's so dark. And one of the thoughts about changing the climate in the near future is it's so difficult to change carbon dioxide because we depend on all the energy generation that produces it. But if you could get rid of black carbon, then that would help to offset some of the warming that's going on.
Talking about soot.
Soot. And in fact, we've already done a lot. You know, the United States refused to sign the Kyoto Protocol, which was trying to regulate carbon dioxide, but we accidentally exceeded the requirement to reduce global warming in that period because we banned chlorofluorocarbons to prevent the ozone layer from being destroyed. So we accidentally met the Kyoto Protocol, even though we were trying really hard not to. But forest fires are making up for this loss of black carbon in the United States. They're becoming more common because the temperature is going up. And, you know, for example, why are we having fires right out here in Colorado all over the place? It's because it's so hot and dry. And so as the Earth becomes warmer, it's going to be hotter and drier, and there's going to be more forest fires. And there is data that shows that the forest fire frequency in the United States is going up fairly rapidly in the last decade or so.
Thank you.
Brown, beige.
Thank you.
Shirt.
For saving my domestic energy costs for my air conditioning, I'm wondering about setting up UV films in my westward-facing windows. Would it be more efficient for my air quality and my heating to block out the heat to put up UV film or to hang up a whole bunch of plants to create shade in my big room downstairs?
In general, the plants sound a lot nicer, but they require maintenance and water. So these are in the details, and this is where engineers will help you. Engineers? No, so don't let your babies grow up to be cowboys. No, let them grow up to be engineers. So this is a very interesting problem. I wouldn't be surprised if you want a combination. And it will be based on architectural, that is to say, how does it look choices. But I'm really glad you're addressing this problem because here's what's cool. First of all, you will save energy, you can feel good about that, but you will save money. And if you have green plants around, it generally puts you in a better mood. But you're from Boulder, an even better mood. Yeah. So I would try, just get started, and there's no substitute for trying it. There's no substitute for an experiment. I mean, architects can do all the calculations they want about plants, but once you start really doing it, you'll know. And I encourage you to plant some food plants in your house, produce, tomatoes or what have you. Yeah.
Thank you.
Thank you for a wonderful, enjoyable, and educational evening. I didn't intend to get smart on my vacation. My question is, in solar energy, what is the more inefficient component, the solar panels absorbing or the battery packs retaining the energy?
Oh, very few people who have solar panel systems use batteries. I live 4 doors from Ed Begley, this guy, Ed Begley Jr. I don't know if you ever watched the show with me and Ed. And on my website, I do have a button, I must crush Ed. I love him, but I must beat him at being green. Keeping batteries on the premises is really difficult. He has what used to be a two-car garage, but now it's sort of like a 1 1/3 car garage, because he has enormous batteries from, I guess they're based on truck 18-wheeler batteries, and it's a little bigger than this table. And it's cool, and it was in the 1990s, and he did it, and he's not going to get rid of it, but it's a lot of messing around. I live on the grid. So that is to say, when I'm making more energy than I'm using, I can go to the electric meter and watch the energy go up the wire. Oh, it's so much fun. But then at night, and in the wintertime, in December and so on, when the sun is low in the sky and there's not as much energy, I have to buy power. Oh, the humanity. Yeah.
So if batteries are not the option for retaining the energy, what is?
Oh, so
Immediate consumption?
Well, right now, there is no moment of the day when our society is making more energy than we're using. No, I mean, I am a drop in the energy bucket. A proud drop, mind you. And it is stupid fun, everybody. My electric bill every 60 days is $10. And that's just fun. Come on. And the cost of my system, everybody, was considerably less than a typical sport utility vehicle. I mean, by half price of a sport utility vehicle. So the journey, though, for the young engineers is to find ways to store energy. And Ed Begley and the technology from that era uses lead-acid batteries, just like in your car, only on a much bigger garage-side scale. But the promise of this liquid metal battery, if this turns out to be the thing that works, is energy densities or be able to store electricity at 10 times that. Be great.
So there's all kinds of practical ways people are attempting to do this. For example, water comes over the dam, you pump the water back up with solar energy and let it come back down again. So you can store energy that way. There are caves in Europe where people are going to put compressed air into the cave, which they make from solar energy, and then they use the compressed air to run turbines at night when it comes back out. In Spain, they have molten phase change material where they take a material and they heat it up in the day, it changes phase, and at night it changes phase back and releases energy. So there are a whole number of different systems being used around the world and being tried around the world to find out what's the most efficient.
The one I'm hot for, you guys, by the way, is hot salt. So this would be regular table salt got so hot it's a liquid. And you heat it up all day with big mirrors in Arizona or some exotic place, and you turn it into a liquid. And then it's still hot all night, and you use it to run a turbine. You make water vapor, make steam, and spin a wheel all night. This is not crazy, but the limitations there, you can't let the salt freeze, as they say, at 1,000 degrees. You can't let it turn back to a solid, or it plugs up all the plumbing, and you got a mess. But the longest journey starts with a single step. Cool. Yes. We'll go for another few minutes, but we're going to have to wind down. Yes, sir.
Oh, okay. Thank you all for your talks, and Bill, I'm a little jealous of your electric bills also. My question is more of a general question. I guess I hope y'all will be able to have a comment on each, I guess, my question. Numerous people have different opinions on the cap-and-trade system in place in countries. What are your opinions on that? And also, what kind of plausible alternative systems can we have in place here in the United States to limit our CO2 emissions?
Well, everybody, the idea is that a cap and trade, you have a limit to how much carbon your country's allowed to make. And if you want to exceed that limit, you trade with a country that doesn't make as much carbon dioxide. You make a deal brokered by or controlled by some organization like the United Nations. The trouble with it is everybody tries to go above their cap. I mean, that's everybody's motivation. So this is where Dr. Hansen's always talking about, no, let's not do that. Let's have a flat tax on all carbon production, all carbon dioxide production. So cap and trade sounds like a good idea, but in practice, it's too divisive. People just can't get along. But it's a start. On the other hand, it's a start. You know, people complain about lawyers, but you need lawyers to figure stuff like that out. And one of the reasons the quality of life is so high in the developed world is we have better laws. You go to countries that have a lot of corruption, it's really hard to make a living. It's really hard to motivate people to patent things and invent iPhones or what have you. So this is a real problem for lawyers. I mean, we like to make fun of lawyers, but this is a real opportunity to figure out a fair way to handle this. Go get them. So how about if we stop with everybody who's in line right now? We'll do these questions and then we'll stop. Is that okay, everybody? So 171.
So part of the IPAT model is population, and since population is constantly on the rise, is it ethical, logical, or efficient to put some kind of limit on that?
On the number of people?
Yeah.
Here's how you do it. You raise the standard of living of women. Then I won't say it's automatic, but that's what does it. No, but I'm not trying to be. You can try wars and worldwide flu epidemics. You can get aggressive, but the best way to lower the birth rate is to raise the standard of living of women. So do you know how to do that? It's complicated. It's really complicated. But it starts with education. And so there are places, I've been to villages in Africa where kids have never seen a magnet. Never seen a magnet. Never made a cell phone call or sent a text message in class. Never seen a magnet. So if we can find ways to educate people in the developing world, that will raise the standard of living of girls and women, and that's going to be, in my opinion, the most effective way to lower the world's population and save us all from ourselves.
And it is ethical to do it that way. To answer your question, it can be a tough question because you're right to bring up population. In a way, it's the crux behind so many of these other problems we have. Here in the West, we're running out of water. Carbonization of the atmosphere we've been hearing about. So many of these other problems are related to population, and it would be so much easier if there were half the number of people on Earth. But how do you do that ethically? And you're right, there isn't any great way unless you do the kind of thing Bill was talking about, and our practices change. And it's actually a fact that in a lot of parts of the world, including the U.S., the population is not increasing, at least not very drastically. We're at a reasonable rate of growth here, and the places where the population is growing out of control are the very poor parts of the Earth. And if you raise their standard of living, then growth rates always drop.
So this is a problem that we will have to face. Right now, the people on the Earth have about 5 football fields each, and that includes the deserts of the world, the ice caps of the world. So you have about 5 football fields to put your house on, grow all your food, and have all those deserts and stuff. And if you go to a time in the future, which is about the same as a time back to the Dark Ages, you will be as close to your neighbor as I am to Bill at the moment. Everybody on the Earth will be shoulder to shoulder in a period of time which is equivalent to going back to the Dark Ages. I don't think you can survive shoulder to shoulder.
Right.
Well, if she's really hot. So we'll do that. We'll raise the standard of living of women worldwide. That's what we're going to do. Let's get her done. Get out there, peoples.
Thank you.
Yes, V-neck black shirt man.
Good evening. A lot of your talks have this undercurrent of negativity that either there's
really
acid, right? Yeah, I know. It took me a bit to realize it, but what motivates you to get up in the morning? What motivates you to actually drive to work and try and I mean, because there's even this sort of irony of like fighting climate change but driving to work to get to, burning fossil fuels to get to work. I mean, what motivates you?
Oh, this is an interesting question. So when I was a kid, we thought the Soviet Union was going to dominate the earth, and India and China would never feed themselves, and that the world would forever be at war. China was a place you could never imagine going, for example. It's so incredibly difficult to get there. So if you look at history, if you just look back at your own life, you'll see the earth is getting better. People are more peaceful, the number of people dying in wars is declining, China can feed itself, India can feed itself, we're solving problems, we're going to the moon, we're exploring the universe, education is spreading across the world, the rate of population rise is declining in time. The earth is getting better in time. It's just that there are lots of problems that are left to deal with, and so we have to face these problems and deal with them. But anybody who looks back, if you look just in the last year, you'd say, oh my God, how can things continue like this? But look back for a short period of time in your own life, and you'll see things have only gotten better in the world in general. They're going to get better in the future, but we're going to have to work at it to make that happen.
So I remember there's a song, thank you, Dr. Tim. There was a song in 1970, and the guy who wrote it died, I guess, 11 months ago. The revolution will not be televised, Gil Scott-Heron, because it was believed that governments would be so powerful they control all the media, and the people would have to rise up in spite of the control of the media. But it turns out that the revolution is being televised.
And tweeted.
Tweeted. Facebook. There was no revolution. I didn't get a tweet about that. Yeah. So that stuff is changing the world for the better. Everybody can communicate in a way that was just not possible even 20 years ago, let alone 50 years ago. It wasn't that long ago where slavery was just accepted and commonplace. So the world, we have the potential to change things because we can all communicate so quickly. And this is what I think about, the great works that we do to control water, these enormous dams, aqueducts. There just will be a time when people control the climate of the earth. There will be a routine thing that we do in some fantastically clever fashion. The difficulty is this next century. We got to get through this next century. So let's get her done. Yes.
Oh, wait, Karen?
Oh, sorry.
I want to hear Karen, what makes Karen get up in the morning?
Oh, yeah.
I love what I do. And even though I portrayed sort of a depressing story, what's great about it is that I get to come places like this and talk to the public and put it into your hands and let you figure out how to affect change.
Oh yeah, well, actually I'm an optimist. I mean, it's important that we talk about problems that we're having and that we don't think that other people are listening to, and so that's what we're talking about tonight. But it doesn't mean that we all think we're doomed. In fact, I think we have a lot of challenges for sure, but as Bill and Brian both pointed out, history is very nonlinear. I mean, like Brian said, in the 80s, we thought the Cold War was going to last forever. We thought we were going to die in a nuclear war. I remember when I was in college going to protests against apartheid in South Africa, and that just seemed like it was never going to end, and it did end. And things change. Humans go through surprising changes that are hard to see coming sometimes. And I feel like even though there's ups and downs, that the fact that we're having a global conversation about the climate, we are having a global conversation about it. We're not all agreeing, but we weren't having a global conversation about it 20 years ago. And that, to me, is the step in becoming an intentional global species. And there are game changers. Like Bill said, there's new technology. We're in communication in new ways with people all around the world. It's harder to hide horrible things. And so nobody knows what's coming, but I certainly don't think we're doomed. And I think that we have some exciting challenges, and we do live also in exciting times of opportunity. And I also love what I do. I get to explore the solar system and try to apply some of those lessons to Earth. And so that's why I get up in the morning.
There you go.
This question is for Dr. Rice, mostly. You're talking about the acidification of soil due to farming, but we have to eat. So, is there anything you see as a good option for us as far as soil quality? No? Okay.
No. I think the biggest thing is we have to work on not over-applying nitrogen fertilizer. It's sort of the mentality that more is better, and that's not true. No. And in fact, the more we apply, the more we make it acidic and not useful in the future. So even though I don't want to talk about policy and regulation, that there perhaps could be some oversight on the use of nitrogen fertilizer.
Perhaps could be. Yeah. Just want to talk about policy.
I'm a scientist. I work for a science agency, and it would be a violation of my position description.
They'd put you in jail. Yeah. They'd put you in jail.
I had dinner with the guy who thought of the word Anthropocene a few months ago in the Vatican, actually. It was a very interesting dinner. And we were talking about what's the next big problem? Phosphates. We need phosphorus to grow organisms and life. It's in DNA, and we don't have that much phosphate available in the world. So that will be your next big challenge to growing food.
So, along this line, how many people buy organic vegetables? So I'd say maybe even most. Yeah, there are ways to farm that don't require this intense. Old style industrial fertilization, but they're more labor intensive, and it raises the price of the food. But if everybody wants it, then that market will be supported, and people pay it, and we'll use land in a different way. I mean, it certainly seems possible.
Thank you.
Plaid man from Plaid.
All right, how's it going? I guess my question is kind of off of David Grinspoon's. We need to make deliberate changes, and some good answers have been made, but I was wondering if you guys could use your imaginations a little bit, and just tomorrow, if we decided, say, just within the U.S., we were going to make huge changes to save the world, what would you guys suggest?
I'm ready.
Bill goes last.
Well, what if we had our government really got serious and we had, the equivalent of the Manhattan Project? We are going to apply our greatest minds and give them lots of resources and really develop the infrastructure for alternative energy and for conservation and support people in changing their lifestyles. We know how to do a lot of these things. It's changed the way that we build the communities we live in, so we don't have to drive so darn much. And to me, it's a matter of our society committing to these things. We know a lot of the solutions. It's just giving the resources to let us go to work and do them.
I have to agree. It's just it's changing the mentality and switching us to a different fuel base. We're going to have to eventually. Why not be proactive and do it now?
So here's what I say. You have to vote. This is the system we have in place. And people have tried a lot of other systems. And as Winston Churchill remarked, it's the worst system possible unless you consider any other one. So in this upcoming election, you don't want to discuss policy. I'm not a government employee. I'm some guy. Just in this election, just take the environment into account. There's going to be people, you're not going to like everything about either candidate, talking about the national election. You're not going to like everything about either candidate in any election. But if you just take the environment into account, I don't think you'll have that much trouble making a choice. And
I was at another meeting. There's another meeting about 6 months ago in which we're trying to look at the lessons of the ozone hole that could be applied to the global warming story. And the George Bush I had a big movie he filmed for us about his views about how he dealt with the ozone hole problem. And the EPA administrator of that time, who was the person that brought in the Clean Air Act, gave a talk there about his inability to understand these people are Republicans. His inability to understand what had happened to his party. The EPA was founded under Richard Nixon. You know, George Bush was the person who solved the problem with the ozone hole and put in the Clean Air Act.
George Bush 41.
Exactly. Right. You know, so why did the party of conservatism, who should protect the environment, suddenly become uninterested in the environment? There's a mystery there. Why, what explains that mystery? How would being conservative and trying to protect the world and the way things are suddenly become opposed to protecting the way things are? This is an inconsistency somewhere.
I just think the pendulum's going to swing. And as I say to everybody, if you don't want to vote, would you please just shut up? But that's not how it goes. The voting is the only thing you get. You've got to vote. You just got to vote. So just consider it. Now you guys, I'm not telling you what to do, but just take the environment into account, because things could change so fast either way this year. I used to think that people would look back, historians would look back on the year 2000 as this big turning point year from a climate standpoint, when Al Gore and George Bush number 43 were going at it. But this year is just as big, but what's happened, everybody talks about jobs. I understand that, but the environment is, to me, a much bigger and significant issue. That's, thank you. Young man, you are the penultimate questioner, the right before the last questioner.
Okay.
Hit us.
Wow, is this really how I sound?
We can hear you, man. Go for it.
Anyway.
We can hear you.
Go for it.
Why do you use uranium for nuclear power instead of thorium?
Why not use thorium?
Yeah.
That's a good question. A lot of people talk about thorium nuclear reactors. There was a very well-known test done about 50 years ago, and it's never really been pursued since then. Perhaps you will be the guy who figures out how to use thorium. It's another radioactive element, not as easy to use as uranium, but maybe not that hard. Anyone?
I believe the Indians are using the thorium cycle because there isn't any uranium in India, and they do have sources of thorium. So there are thorium-based reactors that are being built in India.
And it may be environmentally better, and part of the reason why we don't use it is simply because that was the way the industry started up, and these things tend to get hard to change once you have a whole industry. So it's definitely something worth researching further, and I encourage you to do it.
Go get them. Great question. Great question. Last question. This is it, man. No pressure, no pressure.
I just want to thank all of you for coming out. This has been a very enlightening and fascinating night. And I know I'm not the only one when I say that, Bill, you helped foster my love of science at a very young age.
Thank you. Thank you, man. I love you, man.
I was hoping Dr. Grinspoon could elaborate on, and anyone else who has an opinion on it. It seemed that you felt that there wasn't any good to terraforming Mars, and I was wondering why you thought that and how you approached that idea.
Yeah, so I don't necessarily think that it's a bad idea to terraform Mars in the long run. It may not be, in fact, it may be a good idea, but I don't think we should try it yet. Fortunately, we don't know how to do it really yet. We have some ideas, and people have done some models, and it's a good intellectual exercise. It's valuable that we're thinking about it for the reasons I tried to express. But first, we have to figure out if there are Martians or not. If there are, and there may be, and especially underground, There are, the Martian surface is a pretty hostile place right now, certainly for our kind of life, but at some level underground on Mars there's water, liquid water probably, and well, we have good evidence that there must be. There's ice, and as you get deeper, it's hotter, and there could be something living there. If I had to place my money, I would say there probably isn't, but we don't know that, and certainly there's good reason to believe there was life in the past, and we don't know what it did when the surface changed. It could have gone underground. So ethically, we have to really be careful that we don't
violate the Prime Directive.
Violate the Prime Directive. Do something horrible. But I would also say that if we discover that Mars is lifeless, then there's a pretty good argument that the ethical imperative switches around, and then it's actually our responsibility ultimately, you could say, to bring lifeless places to life. Because if there's a vacant lot next door, why not plant a garden? And if we care about life, and I care about life, I want life to survive, then life ought to be on more than one planet, because if it's only on one planet, then you've only got one lifeboat, and if it sinks, you're in trouble. But if it's on more than one planet, then life has a much better chance of persisting. So right now, we don't know enough, but in the long run, we'll both know how to do it, and we'll know if it's a good idea, and it might be.
That people have done analyses of this problem. I did a work on it about 10 years ago. And as far as we know, there's not enough nitrogen on Mars to support a biota of the scale of the Earth, which is possibly one reason that if there is a biota there, it's not very big and it's hidden, is because there's not enough nitrogen to support a large biota. And of course, you have to hide on Mars right this minute because it's bombarded by high energy particles, because the atmosphere doesn't have enough mass to protect the surface. You can't warm the planet very easily. If you think you're going to warm it from adding carbon dioxide, for example, you're already at near toxic levels of carbon dioxide on Mars now for animals. So you might put enough CO2 there to stabilize plants, but then it'd be toxic for people. And even if you added the CO2, you probably couldn't warm it up very much. So right now, as far as we know, the raw materials are not present on Mars to really terraform the planet in the way we commonly think of it. But I'm sure that we will have terraformed it in the next century, and there will be people living there. They'll be living under bubbles. They'll be living in ice caves. So we'll be living there, and we'll just be in small colonies until we can figure out some way to bring in the resources to do something bigger.
Piece of cake. I always say, if you want to terraform Mars, go live in Antarctica for a year. In the dry valleys, crazy cold, no water, apparently very few microbes. It's just a whole nother thing. You guys, this has been just a lovely evening. Thank you all. I know many of you had to go. Thank you for sticking around. Very much appreciate your support. Pick up a Planetary Society brochure on the way out and let us, dare I say it, change the world. One more hand for the scientists. Thanks, you guys. Thank you.